to stay up to date with the concepts that we are covering, because all of these will be part of the final exam, as you know, right? And if you have questions, please feel free to ask me at any point. So let's get started with today's lecture. This is where we stopped in the last class. We stopped at threshold voltage. And I told you, if there is one concept that we should take away from this lecture regarding MOSFET, it should be threshold voltage. It is that important. Okay, threshold voltage is one of the parameters that we always use to tune circuits, and I will talk about that when I cover the concept of metal semiconductor work function difference in today's lecture. Okay, and I'll show you how that is useful. Okay, so we'll start with this point, and I'll assume, with being a little bit more optimistic, that you have understanding about threshold voltage band diagram in your mind, like what happens at the threshold inversion point, right? If anything, we'll have a very quick revision of that in the next lecture. So I will try to get to the next lecture by finishing up these slides sooner. Okay, let's pay attention, because this slide looks scary, don't you think? It's a busy slide with many notation. So the same approach works. If you pay attention while I'm going through the slide and while I'm drawing, it will be super easy for you to understand, trust me. But if not, then it will be way too much pain to just go through the textbook or even listen to the recording. Who wants to go through a random technical YouTube video again, right? I would rather watch some sort of travel video or cooking video, I don't know. Anyways, so on your left, oh, give me 1 second, probably needs to be paired again. Okay, sure. So on your left, you are looking at not really a band diagram, but individual band structures for 3 different components: metal, oxide, semiconductor. You can only imagine where we are going with it, right? MOS, metal oxide semiconductor. So obviously we're going to connect them together. We're going to have a heterostructure, some band bending to settle down, and then this is what will happen. You'll start with a thermal equilibrium band structure for MOSFET, right? Okay, so before getting there, let's talk about what happens before contact. This will be a very quick revision as well, which is good. Why is this metal? Because you just have a Fermi level, no conduction or valence band. That shows that this is a metal. There is no band gap. You just have Fermi level, right? Okay. Number 2, you see these parameters are marked with some importance. And we talked about these parameters in the heterojunction lecture. I don't know if you remember. There is a difference between, do you guys remember the concept of vacuum level that we used for heterojunction lecture? It's like a really high energy level. If you get to that energy level, electrons are as if they're free. They're in a vacuum, right? They don't even recognize that they're in a lattice anymore. Okay. So we basically use them as a point of reference. We use this level as a point of reference. So the difference, the separation between Fermi level and vacuum level is called work function. Okay. And the separation between conduction band and vacuum level is called electron affinity. We represent that with chi and the other one with phi, because it sounds cool. So you see, we don't have any chi for the metal side. Why is that? Because there is no conduction band. There is no conduction band in metal, right? Metal just at Fermi level. But for semiconductor, you have both. You have conduction band, so you have chi. You have Fermi level, so you can also define phi. Separation between Fermi level and vacuum level is phi, or work function, and chi is electron affinity. Okay. All right. Now, why am I reminding you of all of this? Because we're heading to the next slide, where we'll talk about metal semiconductor work function difference, and all of these parameters will be useful. Before moving to the next slide, let's take a look at this semiconductor. See, it has conduction band, it has valence band, it has intrinsic Fermi level, which is basically nothing, a midway line. And then we have a Fermi level, the actual Fermi level, closer to the valence band, which shows that it is a p-type semiconductor. All right. One more thing. Notice we didn't really pay that much attention to the oxide before, but now we can take a look at it again. This is the oxide. you should immediately notice that conduction band and valence band are farther out in an oxide compared to the semiconductor. And I told you so, remember? Oxides have huge band gap. That's why they're oxide. That's why it's so difficult for us to create an exciting electron enough to send it back to the conduction band for conduction. So that's why oxides don't really conduct electricity, because it's so difficult to excite electrons to make them go to the conduction band, as opposed to the semiconductor. So essentially, between semiconductor and insulator, there is not much difference in terms of band diagram, except the fact that one has a huge band gap. Okay, now having all of this thing in mind, what is the work function for metal? Phi m, as you see here, phi m is the work function for metal. And you also see that marked here. This is taken from the textbook. Why do you have an E with the side with phi m? Because it's in electron volt. If you divide something with, do you remember this? Electron volt is an unit of energy. You could either represent it in joule, then we could have just written phi m in joule. But if you want to express it in electron volt, just multiply it with the charge of electron. You get electron volt, okay? All right, now, how about the work function for semiconductor? How will that look like? This is the work function for semiconductor, okay? The difference between the Fermi level and the vacuum level. So I'm looking for, get to the next slide. I'll get back to this. I'm going to look for metal semiconductor work function difference. This is a very important parameter. It's a mouthful, I know, but you can express it as phi ms, the work function difference between metal and semiconductor. That's why ms, not master of science, material semiconductor, okay? All right, anyways, so we'll get to that. That's why I'm talking about these two parameters so many times. You might be wondering, what's wrong with this guy? Like, why is he pointing out semiconductor work function and metal work function so many times? Because I'm going to do a math right now, and you are going to do it with me. This is phi m, this is phi s, and this is going to be pure geometry. So please pay attention and help me write an equation. If I write phi m minus phi s, okay, take a look at the image. How much in terms of geometry, just think about geometry, right? These are all drawn to scale, for example. How much area is left when you take the difference? You get this much distance, don't you think? If you subtract, or whatever, phi s minus phi m, if you take the magnitude of it, if you take the magnitude of it, don't worry about negative sign, okay? Negative or positive, doesn't matter. The difference is this much, don't you think? Work function of the metal, work function of the semiconductor, take the difference, this is the difference. Could you help me find that difference using math, just using pure math? Okay, let me define phi s with some parameters that we know, okay? Here goes. This is chi, as you see already marked. Chi is the electron affinity, which is a material parameter. So we're trying to express it in terms of material parameter. Can I also add this? Let me show you. This is chi, and then this is, can I say this is band gap over 2? Half of band gap, because intrinsic Fermi level is midway between the band gap, right? Okay, so, and then how much do I need to go? This much. Can anybody tell me what this thing is? That will show how many of you remember. We talked about the difference between the Fermi level and intrinsic Fermi level many times. Let's go back to this slide. Notice, Fermi level, intrinsic Fermi level. This parameter is called phi f n if it is an n-type semiconductor, or phi f p if it is a p-type semiconductor. So the difference between Fermi level and intrinsic Fermi level is an important parameter. And there was even equations like this that helped us calculate that difference, by the way. Notice? So That's the reason why you should remember or review. Make sure to review. Okay. So this is phi if N or P. P, because it's a P-type semiconductor. So there are three parameters: chi, band gap over 2, and then phi FP. Can I write that phi S, which is, let me show you with a different color, maybe red. This is phi S. Phi S would be chi plus EG over 2 plus phi FP. Can I write it? Just looking at the geometry. Any problem? This is your phi S. If you try to get phi S minus phi M or phi M minus phi S, whatever, like the difference between the two, you have to subtract phi M from this, don't you think? Okay. Okay. So the reason I'm telling you this is because fast forward and get to this equation. Look at this equation. Chi plus EG over 2 plus phi FP. This is what? This is phi S, as we just noticed here. Is that right? And then, so basically here we calculate the metal semiconductor work function difference. You take the metal work function and subtract out the semiconductor work function. And this is basically semiconductor work function. This equation is coming and I'll talk about it. I hate to talk about it using this diagram, which the textbook does, because it makes it more complicated to explain and understand. Okay, but I believe this diagram makes it super easy for us to derive. So I typically use this, and I got this idea from one of my professors at Penn State, Professor Jackson. I really like him, as you can tell, because I keep referring him. So he taught us, hey, why are you doing this the wrong way, like the difficult way? Why are you trying to eat rice like this? Why don't you do it this way? Like, okay, that's honestly, you could have used this pre-contact band diagram rather than using post-contact band diagram where everything will be bent, right? When the bands will bend, right? So that's why I'm getting ahead of myself, showing you that you could derive it using this band diagram. Do you need to derive it? No, it's okay. You don't need to. It has been derived. I'll give you the equations, but it's good to know how it comes into being because it's such an important parameter. Okay, at some point in your career, if you choose a career in semiconductors, you'll have to deal with it. So it's better to at least know where it comes from, so that even if you forget, you could go and look it up and do the exercise that I've done in class and do it by yourself and figure out, oh, I see, it makes sense. All right, now this is pre-contact. When you put these three materials in contact, I hope you guys know this by now, bands will bend, right? Electrons will redistribute to achieve what? To achieve a common Fermi level. Notice the Fermi levels were not in the same place before. Here and here, there are two different locations for Fermi levels. When you put them together, the overall system will have one common Fermi level, and that's why in trying to achieve so, bands will bend. We did that many times. I'll do it one more time. So it's so important, and I'll use the trick that Professor Jackson taught me again. So when these Fermi levels try to come towards each other, this one will go down and this one will go up. Don't you think? They will all contribute. And I told you that these other bands in the semiconductor are like sticky. They're basically stuck here at the edges. But the rest will follow the Fermi level, right? If the Fermi level goes up, all the other bands will go up with the Fermi level. Now try to visualize. As this Fermi level goes up, this conduction band will go up, this valence band will also go up. So that's what you see. Conduction band has gone up, valence band has gone up, Fermi level has gone up to match up with the other Fermi level. But while these are going up, what happens to these two edges? Don't you think they will be bent like this if the other two edges are stuck? Does that make sense, folks? So that's the reason why these bands bend this way. Okay, and you have a common Fermi level at thermal equilibrium. And one more thing to notice, which we didn't really discuss that much before, what happens to the oxide? Remember, And I think I told you before and that this is only a trick to remember. This is not the physical reason, okay? How many of you remember that we derived the electric field and voltage inside a PN junction diode's depletion region? Do you remember that? And I showed you, you do double derivative, use Gauss's law to derive, like you can basically understand the shape of the band diagram by going through those maths. Okay, so we could always derive it mathematically, but we are not going to derive it for every band diagram we draw, right? So it's much easier to understand or remember it using a trick. But deeper down, you should understand that this is all related to energy minimization eventually. Okay, now why am I telling you this? I'm going to tell you one more trick. The direction of bending in the semiconductor will be the same as direction of bending in the oxide. So notice this is the oxide band diagram. So we basically had conduction and valence band, right? Notice the band has bent, conduction band, and there will be a valence band here. It is so down, like it's not even visible in the picture, right? It's basically farther down. The valence band is so low. But notice the oxide will also bend either this way or the other way, depending on which direction the semiconductor is bending. So let me use a different color here. If the semiconductor bends this way, the oxide will bend this way as well. Question is why? Remember, this is the bending. Band bending represents charge. Whenever there is a bending, there is a type of charge, either positive or negative. Still with me? Okay. And that represents electric field, the direction of electric field. Okay. Notice, you remember that we basically took the bending and defined something called surface potential phi s. The amount of bending basically represents the potential. And potential has positive and negative polarity, like, and direction, right? Electric field has direction, as you know. So the direction of electric field has to be the same here and here. That's the reason why the bending is similar, because the oxide typically follows the electric field in the semiconductor. Okay. There are exceptions. There are some unique fancy devices that people developed, and I worked with one of them in my PhD. It's called a negative capacitance transistor. That could actually break this rule. But without that, I mean, chances are you will probably not have to deal with it in regular form. Okay. So it could be a general rule of thumb that the oxides will always bend in the same direction as the semiconductor. So I hope you can easily remember it now. All good? Don't worry. I'm going to fast forward through this because we'll have a practice in the next lecture that we start today. Okay. So in the very first slide in the next lecture, we'll review all this very quickly because there is a reason. There is a different message, but we'll also need the band diagrams. There is no getting away from band diagrams, unfortunately. You like it or not. This is something that we have to live with. Okay. Now, see, this diagram looks really busy and scary, but I'm going to go through each one of these components one more time to prove that this is not really scary. We have covered all of this. You know this. You just have to understand and trust yourself that you know this. Let's start from the left and go to the right. Okay. On our left, this is phi m, which is metal work function, because this is the vacuum level, by the way. The way this diagram works is when all these bands bend, the vacuum level is also bent, basically. That's how we show the vacuum level. Okay. So that's the reason why, you know, you see that this line is bending. Okay. But I think this is very confusing. So you can, for all practical purposes, ignore the vacuum level because this is a hypothetical level anyways. It doesn't really exist. Okay. This is much easier to understand when the vacuum level is flat and all the bands are flat. So you're basically following along. But when these bands start bending, the vacuum level will also have to follow along. Okay. Why, you might ask? Say, for example, phi m is a material parameter and chi is a material parameter, right? If this guy bends and the vacuum level doesn't bend, so in that section, notice you'll have a different chi. Don't you think? The difference between the conduction band and vacuum level will change, which is not true, which is not possible because it's the same material. So you have to bend the vacuum level accordingly to show that the separation remains the same. Okay, that's the reason why the vacuum level follows the bending. And they don't even draw the vacuum level here in this side, actually. to avoid confusion, but I think it's even more confusing. Anyways, you could essentially ignore this part of the band diagram and just focus on what I'm drawing here. Fermi level, oxide, and semiconductor. Simple. The rest are just notations. And all the notations are basically the repeat of what you see here. Okay? Take a look at it at home. And if you're still confused, come talk to me. One thing that I want to highlight from this diagram, and the reason why I still have this diagram, despite it being confusing, is because what does this amount of bending mean? Anywhere, if you see a bending in a band diagram, you could measure voltage from that bending. Remember, we basically use the bending in the semiconductor to calculate surface potential, right? Amount of bending represents surface potential. Similarly, the amount of bending in the oxide represents the voltage that appeared across the oxide. If you remember my last class discussion, when you apply a gate voltage, a portion of the gate voltage is dropped across the oxide, and the other portion actually appears at the surface and does something, right? So this is essentially a loss. An oxide will lead to some sort of voltage loss. And this bending, amount of bending, shows you how much voltage is being dropped across the oxide. A quick question hopefully will help solidify the answer. This is the red oxide, this is the green oxide. Which oxide do you like? Let me ask you this. Depending on the bending, okay? So for the same amount of everything else, you have more bending in the green oxide than the red oxide. Which one is better, in your opinion? What does the amount of bending represent? The voltage drop across oxide. Which one has more voltage drop across? Which one has more bending? The green one. So it has more voltage drop across it. Do you like to drop voltage across oxide? Is that why you are making the device? That I will drop voltage across the oxide? No, this is basically a loss, right? You have to use oxide. Sure, you have to live with it, but then it drops some voltage. So the less drop you have, the better it is. You see that? So that's why you should pay attention to the band diagram, because that clearly shows that there is a drop, and you could measure the amount of drop, and you could do something about it. You could choose the oxide accordingly, or you could tune the oxide parameters accordingly. All right. Without further ado, I'm going to move over to the next slide, because otherwise it's going to be super boring just looking at the same diagram. Switch over to a different concept. And remember, simply because I'm switching over to a different concept doesn't mean I'm evading the challenge here. I know it's challenging to understand. I encourage you to review this at home. Sooner you can do it, the better it is. You don't want to leave it for the last moment when you're preparing for your finals, and then you're trying to solidify fundamental understanding. No, do it as soon as you can. Maybe this week, maybe this next week, maybe the week after that. The sooner the better. And then come talk to me and tell me that, hey, I didn't really understand this section. Tell me more. And I'm more than happy to do so. That's actually one of the things that excites me, to dig deeper into a topic with other students. Okay, now getting back to this diagram. These are all taken from textbooks, and I'm not bringing in any exterior material, trust me. So we have to cover the textbook. So the textbook talks about polysilicon gate, which is basically like a history, by the way. We no longer use polysilicon gate. I'll tell you about it in a second, but they used to be the mainstream gate material at some point. Couple of decades ago, by the way, what is polysilicon? So polysilicon is basically silicon, but heavily doped silicon. So polysilicon gate is basically N plus or P plus. See, notice this, N plus poly or P plus poly. It's polysilicon, basically silicon, but it's heavily doped. So when you heavily dope a semiconductor, it almost becomes like a metal. It's heavily conductive. So instead of a metal, you could use silicon, a semiconductor. Why, you might ask, why would you use a semiconductor? Why don't you use a metal? Because it's difficult to handle metal. Have you ever considered that if you put in a metal contact on top of a semiconductor, will it stick properly? Wouldn't it just move over and just, go away? Have it ever? What makes do? We don't use any glues to put materials together, okay? Metal oxide semiconductor, metal oxide semiconductor could be silicon. One thing is kind of given, the oxide is silicon oxide. So basically Burn, when something reacts with oxygen, it's basically burning, as you know, right? When you burn or like heat up silicon, the top surface becomes silicon dioxide. So this is more like obvious that silicon oxide and silicon will have a really nice solid interface. Silicon oxide will not just go away. But the metal could be anything. Why would the metal just stick there on top of oxide? Wouldn't it just move away? Don't you think? So it's very challenging. It doesn't sound like much, but it's very challenging to keep a metal on top of an oxide. So people dealt with these challenges in fabrication. So they decided, instead of doing so, let's just use silicon again, which is much easier to have stick on top of silicon oxide. Silicon oxide, silicon. Really nice combination, dealing with only silicons. That was the reason why people used to use polysilicon at some point. How do you know? How can you tell, looking at the band diagram, how can you tell that this is a polysilicon gate versus a metal gate? And all of these are challenging, interesting questions for interviews, by the way. I don't know if you have ever taken any interviews with any tech or semiconductor company. I mean, one of my graduate students recently took the interview. He didn't believe me, by the way. Nobody believes their advisor, typically, until they go through the process. I told them, this is highly technical. Industry folks don't care who you are, how big your CV is. They will just get into questions right away. And he told me that. Basically, they called me, are you so-and-so? Yeah. Question. They didn't even ask you, how are you? Well, typically, it's not really that bad, but they would ask you, how are you? How are you doing? And then get into question. But that guy was probably crazier. But they ask you questions. And one of the questions could be, when you go to one site, hey, do you think this is a metal gate or a polysilicon gate? Let's see whether you can answer that question. Look at this one. Will a metal ever have conduction and valence band? No. Easily you can, it's easy for us to understand that this is a semiconductor. Okay, and this is oxide. This is again semiconductor. So this is again semiconductor. So basically you're using polysilicon gate. This should be the gate. Okay, and this is N plus. How do you know? Because the Fermi level is at the conduction band. I hope you guys remember that. Degenerate doping, we talked about it, right? And this is P-type semiconductor because the Fermi level is at the valence band. They haven't even drawn the conduction band because it's basically they have drawn it, but they haven't marked it. Like this is the conduction band. How do you know? Look at the band gap. This is the band gap. That's why. It's as if we are like debugging a code, right? Still with me? Okay. So I think band diagrams are fun, honestly. Initially, they're super boring. They're crazy. But the more time you spend with them, you see that they basically have a lot of clue about devices. So oftentimes when you deal with like something fancy, we come up with the band diagram and then sit with the band diagram instead of looking at the device structure, because that tells us a lot more about the underlying principles. Okay, moving forward. Nothing else changes between these two diagrams. The only difference is N-type, it's P-type. That's all. Okay, so this slide introduces the concept of polysilicon gate instead of metal gate. So I wanted to cover that still, so that you know that polysilicon gate is possible. Is it good? I mean, if it were good, why would we switch to metal gate in the modern generation, right? The metal has to be better. So we figured out a way to have metal stick to the surface. That's why you have metal gate. Somebody might ask you, or I'm going to ask you, familiarize yourself with the term HKMG, high K metal gate. This has been the technology for the last couple of decades. So all of our transistors, even the most advanced ones, the ones that are not covered in textbooks, by the way, they're all HKMG technology. HKMG stands for high K metal gate. So at some point in technology, in early 2000, like 2005, 6-ish, slightly before that, people switched over to using a different oxide instead of silicon oxide. We have started using hafnium oxide, okay, instead of silicon oxide. We will not cover the reason here in this course. I typically cover it in 433, but doesn't matter. There are reasons. So we switched over from silicon oxide to hafnium oxide. And high K, what does K means? In a capacitor, if I write the equation for capacitance, parallel plate capacitance. You have epsilon naught A over D, and there is a K. K represents dielectric constant, right? Dielectric constant for a material. For silicon, it is something, say 3.9. For some other material, it is something else. So for silicon oxide, K was around 3.9. For hafnium oxide, it's about 24. So can I say that hafnium oxide is a higher K oxide? Like an oxide with higher K? So the name stuck. I mean, people started calling it high K oxide. So that's why HK. And then people started using metal gate instead of polysilicon gate. So MG. This is a jargon that semiconductor industry uses. So you're in the HKMG technology. If you go to conferences and somebody is presenting, they will probably use this without even realizing that people might not even understand this. It's so common. Okay. So don't worry about this slide too much. Let's move over because we talk about HKMG. And immediately we switched over to metal gate again. Forget about polysilicon. Okay. Now, that brings me to the slide that I was a little bit worried about. And that's why I kind of went ahead of myself, used geometry to derive this equation. Remember, this slide is in the textbook to first of all scare you and then eventually derive this equation in the hard way using a vacuum level that is not, uniform. That is like folded vacuum level instead of uniform vacuum level. But it is much easy to derive the same equation pre-contact using uniform vacuum level. And that's what we did in the class. Okay. You can forget about it if you want to. I'm giving you the license to do so. But please remember that this is how it comes. It's not a random equation that just comes out of the sky. Okay. This equation is metal. It gives you the metal semiconductor work function difference. Why should we care about it? That's the most important question that you should remember. So now that we are dealing with HKMG technology, we have metal gate. When you connect a metal with an oxide and there is a semiconductor on the other side, this overall system will have to balance out its Fermi level. And in doing so, you noticed this thing happens. There is a bending everywhere in the oxide and the semiconductor. Metal never bends, by the way, because Fermi level, notice Fermi level never bends. Conduction and valence bands will bend, right? Fermi level is a hypothetical level. Now, the moment you connect the metal, you haven't even applied any voltage. It's all zero voltage, by the way, zero applied voltage, thermal equilibrium. But then there is a bending. Might be, wondering what's wrong with bending. I mean, it's okay. Like, let the semiconductor bend. What's the big deal? Did I tell you whenever there is a band bending, there will be charge accumulation. Okay. So apparently that charge will have an effect on the device property. If you connect random metals, there will be different kinds of bending. For different metal, there will be different amount of bending. So you have to find a way to quantify how much bending will occur in the material. Take a step back for 30 seconds. And let me tell you why we talk so much, use this math and Venn diagram so much in semiconductors. Because devices are so small, they're smaller than virus and bacteria. You cannot see them. How do you know? How do you probe and see what's going on inside the material, inside the device? There is no way for you to know. So from the Venn diagram, you have to predict what's happening. And, you see the point? Mathematically and theoretically, explain what could be the reason for the devices to behave a certain way. Okay. Now, even without applied voltage, bands bend, which is very problematic for us to derive any theory or track their property, because they could all bend in different directions. And then it will be difficult for us to control them. You have billions of devices. If they all randomly bend in different directions, it's a nightmare. You cannot control any of them, right? So you have to find a way to quantify the amount of bending and then reverse the bending to make them flat. That's where we are heading, by the way. Flat band voltage. See, there is a slide called flat band. So I'm heading towards flattening the band. Okay. So we need to first quantify how much bending will you get. That's what we can calculate using metal semiconductor work function difference. So turns out the bending is related to the work function difference between the metal and the semiconductor. If there is no work function difference, no bending. If there is work function difference, when you try to flatten out the Fermi level, there will be bending in the band. Okay, so by calculating the phi ms, you can calculate the amount of bending. Once you pre-calculate the amount of bending, you could also calculate what you need to do to flatten the band before you begin operation. That's called the flat band voltage. I'll show you gradually. First of all, this is the equation that we derived together for a semiconductor with, p-type doping. As you see, this is p-type semiconductor. The other diagram looks equally scary. Is the same, exactly the same thing for n-type semiconductor. So obviously we're not going to go through it. As you see, the equations are quite similar, except for some signs like plus and minus, that's all. And also, instead of phi fp, which is a signature for p-type material, you have phi fn, which is a signature for n-type material. That's the difference, right? So I'm not going to go through the derivation for this again, but hopefully you have some peace of mind saying that if we need to, we could derive it, but never derive it using this, band diagram. Use it like pre-contact. Okay, now to give you better news, even better news, we no longer have to calculate. This was done when people just were looking at the semiconductor fabrication process and trying to figure out what to do, how to manage it. And they figured out, engineers figured out, they found equations. So we no longer have to deal with this anymore. We could always just look at a chart like this. So phi ms, which is the metal semiconductor work function difference, for different metal, gold, aluminum. This is obviously not a conclusive list, as you can tell, right? This is a sample. So you have graphs like this. In semiconductor industry, you no longer have to deal with those equations. You basically just plug in numbers from this. Okay? And notice, we are plotting it against doping concentration. N stands for doping concentration, okay? And by the way, why is NB? B stands for body, because this is the body. This is also called the body terminal. Okay? Semiconductor terminal is the body terminal. It could be N-type or P-type. So instead of writing N donor or N acceptor, we are just writing in body doping concentration. Now, notice one thing. There was phi fp and phi fn in both equations. The others, band diagram is a material parameter. Chi is a material parameter. Phi m, which is the metal work function. You might be wondering, hey, hold on. I mean, I expected a question. I got that question, actually, by the way, last time I taught 335. Somebody asked, oh, so you are finding metal work function and subtracting semiconductor work function. You did all those to, break semiconductor work function down to small scale components, but you didn't do anything for the metal. Why is the case? Because metal work function is very easy to experimentally measure. Photoelectric effect. Remember Einstein's famous Nobel, experiments. The reason why he got the Nobel Prize for explaining that. Super simple experiment. You could always do an experiment and calculate the metal work function. It's easy to get. And how many metals do you have, right? We could always look at a chart and just plug it in. We don't care. But semiconductor work function is more complicated. You know why? Because of this phi fp. Metal work function cannot be controlled. It's given. Take it or leave it. Copper, this is the number you leave with. Silver, this is the number you leave with. So it's not really that interesting. Semiconductor work function, you cannot do anything with chi, you cannot do anything with Eg, but you can do something with phi fp. And notice this equation. It's also given here. We have been using and throwing this along different slides, by the way. Notice there is a doping concentration sitting in the equation. By changing the doping concentration, you can change this parameter. So semiconductor work function can be tuned and tailored. That's why we love semiconductors. You can control everything. Making sense? That's the reason why. I mean, if you had asked this question, I would have answered. You didn't. So just imagine how many more information you're missing out by not asking questions, right? I mean, I'm happy. They didn't ask me. I'm good. Just look. The problem is I have to finish the syllabus. So oftentimes I could be selfish and move away. But I feel bad. I want to give you the answers. So that's why please ask questions. Okay, now. Still with me? Okay. Now, that's the reason why we are plotting it against doping concentration, because phi ms, metal semiconductor work function difference, is a function of doping concentration. In fact, that is the only parameter you can manually tune. Others are all material parameters. You cannot do anything about it. The only thing that you can tune is phi fp, but not really phi fp. Phi fp is being changed by doping concentration. So that's why this diagram shows, what happens with respect to doping concentration. All good? Let's see what does this in your exam, by the way. You might have to use this chart to extract phi ms. So if I tell you that we have a MOSFET with gold gate contact on top of n-type silicon, okay, and blah blah blah, calculate so and so, so and so. For those equations, you have phi ms, and you have to find value of phi ms. How can you do it? Okay, let's see. Where is gold? There is gold. There is gold. Yeah, these are the two golds. And I asked for n-type silicon. There is n-type silicon. So this is the graph you should look at. Okay. And then you can see maybe I told you that the doping concentration is 10 raised to 16. So for 10 raised to 16, what is the phi ms for gold? You can, extract the number. It is also possible to calculate the number, by the way, but trust me, nobody cares. I'm not going to test you on that. Anyways, it's just putting in numbers and calculating. Doesn't change anything. Okay. That's all good with me so far? Nowadays, we have database. You don't even have to worry about it. We have database. Just search for something, it comes up. You don't even have to do this manual labor anymore. Like, okay. But in your exam, you might have to deal with it. Okay, so these two equations will be vital. Even if you forget about this internal details, still have to deal with phi ms. One more question that I got, and I want to answer. Nobody asked me, why is there prime everywhere? Why are you writing prime? Good question that you didn't ask. So typically, whenever in any semiconductor equation, whenever you see a prime on top of it, it typically represents per unit area. Okay, we often calculate. Are you guys still with me? Okay, but not here. Not here. So for example, in most cases, a prime often represents per unit area for capacitance, for example. But this is different. This represents, notice, we had a phi m. We had a phi m before, and now we have a phi m prime, which is like an effective phi m. So apparently, when you go from pre-contact situation, just to answer this question, this is phi m. This is the real phi m. This is the phi m that you get out of, say, chemistry charts. Say, but when you connect these materials together, they all bend and the bands reshape themselves, right? So then you could define phi m again with respect to the oxide energy level. That this is phi m prime. Notice that this is the real phi m. This is phi m prime. So when you derive with post-contact band diagram, we deal with the primed quantity, not the real quantity. Okay, but are you guys still with me? But essentially, it's all the same if you just deal with real material parameters pre-contact. So don't worry about what the textbook is doing here. They're using post-contact, parameters. That's why they're using prime. That represents post-contact. So chi is not the real chi. Notice the chi is being defined with respect to the oxide. They have assumed that the oxide top layer is the vacuum level. It's like a assumption that they made inherently. Okay, and that's why they have defined an effective chi, which is chi dash, with respect to oxide. See, a simple question, but more complicated answer, which took at least 3-4 minutes of my time, right? But it's worth it. I mean, you might have a confusion at some point in your life. Summary, just keep in mind that phi ms matters. You get phi ms either from a chart or from a database, but you can control phi ms. More importantly, how can you control phi ms? They're not going to test you on these equations ever. They're going to test you on your understanding of how phi ms can be tuned. By changing what? What is the only thing that you can change to change phi ms? Tell me. Doping concentration. Thank you. See, like when I taught n-type dopant for the first time in class, the very first few lectures, p-type dopant, it seemed like such a meaningless concept. Just knock out a silicon with an atom and like, okay, what's the big deal? But see, it's everywhere. This is controlling everything in semiconductor doping. Okay, moving forward. After this slide, you'll understand why phi ms is such a big deal. Okay, after this slide. Okay, here is what I already told you about, but this will be a repeat, which is a good thing. When you apply a gate voltage, notice when you apply a gate voltage, a portion of the gate voltage drops across the oxide. The oxide takes a share. And notice this is Vox. I don't know if you can see it, but if you zoom in, this is the oxide voltage. And then a portion appears across the semiconductor, which is the good part. This is what we like. Maybe I should use green here. This is what we like. We want the voltage to reach the semiconductor and do something, right? And that's what you see here. This is the band bending in the semiconductor. Basically, it's all the same if you measure it here or here. Doesn't matter. The bending will be the same. Still with me? So this is good. But then there will be another part that will drop across phi ms. Like to balance out the work function difference between the metal and semiconductor, a portion of the voltage will be gone. Like you use your gate voltage to do something to the semiconductor, but they will say, hold on, our work functions don't match. Metal and semiconductor work function don't match. So a portion of the voltage will drop or will be spent in trying to balance out the work function difference, which we hate even more, right? As you see, right? Okay, so that's the other reason. That's not the only reason. Engineers find out ways to convert limitations into features, by the way. So they found out a way. If we were to live with metal semiconductor work function difference, let's use it to our advantage. And I'll tell you the advantage in a sec. But does this equation make sense to you? Okay, this is an equation. This is an old band diagram that we saw before. By the way, this band diagram is interesting to me, at least, because it shows you a new information. Every time you look at the same band diagram, maybe there is something new here. Can anybody notice what changed here in this band diagram? What more information can we get? Notice the Fermi levels are not fully aligned, are they? So it's not thermal equilibrium. Whenever the Fermi levels align perfectly, that's thermal equilibrium. It's not. That means we have applied a voltage. How much voltage have we applied? If you remember the diode lecture, remember we could find the difference between the Fermi levels in two sides and calculate the amount of voltage applied. There was a question in the midterm exam about it, wasn't? Right? So similarly, look at the Fermi level here. Look at the Fermi level here. Calculate the difference. That is how much voltage you have applied. This is Vg. So you can calculate the applied voltage from this band diagram. All right. Okay, so move over to the next one. Okay, look at this band diagram one more time, please. This one. And tell me, what should I do to try to balance out and make these bands flat? And then I'll tell you the reason why we care about flattening the band later on. But I want to flatten the band. Okay, so you have to basically, when you apply positive voltage, the Fermi level goes down and the bands bend in that direction. When you apply negative voltage, Fermi level goes up in this direction. And I'm fast forwarding, but I seriously hope that you remember that. Remember, I use this analogy of when you apply negative voltage as if you have a helium balloon. It takes up the Fermi level, right? When you apply positive voltage, you have applied some weight and Fermi level goes down. To help you remember, the same concept applies here. It didn't change. So basically, when you apply negative voltage, the Fermi level will go up, and then these bands will start following up and basically follow, the direction of the applied voltage, apparently. So now that is already bent down, to make it bent up, you have to apply a voltage in the other direction so that it flattens, basically. So you have to apply some voltage to, let me just zoom into this section again. Notice, if the Fermi level were here, exactly the same everywhere. This would be thermal equilibrium. Okay. At thermal equilibrium, you don't get flat bands, you get bent bands like this. Still with me? When you apply a negative voltage, that means it goes up, the Fermi level on this side goes up, these bands flatten. But I mean, you need to know how much to apply. If you apply too much, it will bend the other way, right? You have to apply exactly the amount that is necessary. That amount, the amount of voltage that you need to apply to just flatten the band is called the flat band voltage. This is a gate voltage that you need to apply to flatten the band. You might be wondering, what's with all this flattening the band, right? Remember, when you flatten the band, that represents zero charge in semiconductor. So semiconductor is perfectly balanced. And then after that, you bend either this direction or the other direction, which defines accumulation or inversion. So that helps us control the properties of a MOSFET. If you always start from flat band, you could easily change the direction of the bending in one way or the other, and then control the MOSFET the way you want. So if you know exactly how much voltage to apply to flatten all the bands, that gives you control over billions of transistors. If not, they will all be bent in different directions. Okay, are you guys all with me so far? Okay, so flat band voltage is like a reference voltage. It's like zero or origin. That's where we start, not at zero. We don't start at zero gate voltage. That's what I'm trying to get into. Even when you apply zero gate voltage, things are not nice and flat. Things are bent and full of charges here and there. So you have to bring everything at perfect zero charge balance. And you do that by applying the flat band voltage. And you can calculate it in different ways. You can figure out the flat band voltage either through calculations like what we're doing here, or there are experimental ways of figuring out flat band voltage. And I'll tell you that, I don't know, maybe not in this particular lecture, but in the next lecture, we will talk about how to experimentally calculate flat band voltage. So I'm giving you the difficult part, which makes it looks like, oh, all hell is breaking, on me. But then there is an easy way. People figured out a way to calculate flat band voltage with experiments, and then you no longer have to deal with all those fancy maths and stuff. But you have to deal with it at some point. Now, one more thing to notice, even at flat band voltage, oxide, this is deliberate, is not flat. I mean, oxide could also be a little bit bent. So there could be that represents there could be residual charges. Whenever there is a bending in any direction, in any layer, whether it's in oxide or semiconductor or wherever, you will understand that there are some charges, positive or negative, depends on the direction of the bending. Okay, but there will be some charges. Question is why? You might be wondering, hey, the semiconductor is flat. We care about the semiconductor being flat because the semiconductor changes from accumulation to inversion, not the oxide. The oxide is basically useless here in terms of, conduction and stuff. But oxide can still have a bending and residual charge because oxide often have trapped charges in them because of broken bonds. No material is perfect. There will always be broken bonds. And because of that, typically these are positive charges. There could be some exceptions, but typically these are positive charges. So even when you flatten out the bands, oxides could still bend. We don't care. It's fine. Still with me? This is also another popular, exam or interview question. All right. Now, this represents flat band condition. There are different ways of looking at it. Band diagram, charge diagram. This is called charge distribution diagram. This is also a very popular way of representing activities. You apply positive voltage. So you have positive charge in the metal. Paying attention? Basically, you apply voltage, you create charge in metal, and the charge is shadowed by the charge in the oxide. Charge in the oxide. And there is no charge in the semiconductor. Like any blue region is charged. For reference, let me just move forward and show you. If there is charge in the semiconductor, there will be blue region in the semiconductor. Okay? Blue region represents charge here. So notice, going back to the previous section, there was no blue region in the semiconductor side. that represents there are no charges in the semiconductor. Why? It's flat. But there are some charges in the oxide already, which you see here, because there is some bending. The exam question would be, interview question could be, okay, if I give you a flat band diagram, maybe you are lucky. You have a perfect oxide. Maybe you're lucky. Then what will happen here? This is not going to be there. No charge in the oxide because it's flat. Perfect oxide, right? But because of broken bonds and imperfection, there are some internal trap charges, fixed charges in oxides. And that shows up here. We often represent it as surface charge, QSS, surface charge. Why? Because the broken bonds typically occur at the surface. Whenever there is a surface, there are broken bonds. Okay? Because you switch over from one material to the other. You change from silicon oxide to silicon. And that's where all the problem occurs. That's where you have broken bonds. Okay, that's why you have charges. All right, now notice flat band voltage can be calculated, is basically a function of metal semiconductor work function difference. Oh, surprise. And the surface charge in a semiconductor, in an oxide, sorry, and the oxide capacity. Okay, still with me? Surface charge in an oxide is basically you don't have any control over. You cannot change it. Oxide capacitance you can change by changing the thickness of the oxide, but oftentimes the thickness is fixed. It is dictated by the technology, so we don't really deal with it that much. But phi ms is a very popular parameter to change. To change what? To change the flat band voltage. I mean, I see you're all like silent. Are you guys still okay? Feeling okay? Thank you for being honest. Where did I lose you? Okay. Okay. All right. Let's take a step back. We have seen phi ms is important. We talked about flat band voltage, which is an important parameter which shows where the bands become flat. Why? Because that's where we want to start our operation. So our operation will always start at flat band and then go up or down in either direction, depending on what we want to do. So that's why we need flat band. So there has to be a way to control the flat band voltage, right? And how do you control the flat band? You control the flat band by controlling phi ms, which is metal semiconductor work function difference. So these two parameters are linked. It's kind of like a detective story. You don't realize it, but basically it is what it is. We realize phi ms exists. That creates a problem. Okay, we'll deal with that problem. Then we realize flat band is an important, concept to keep in mind, and they are linked together. And I'm gonna make the punchline in this slide because that will link all three of them together. What is VT? How many of you remember VT? Threshold voltage. That's where our last class ended, right? I told you threshold voltage is the point where the transistor channel opens up. You create a channel and you start conducting current through the channel from source to drain, right? So threshold voltage is the point where the transistor turns on. And the whole purpose of the transistor is to either turn on or stay off. When it turns on, it represents 1. When it stays off, it represents 0. And in digital universe, we deal with 1 and 0. If it is on, it's 1, otherwise 0. So basically, it changes the bit entirely from 0 to 1 by changing from being off to on. So the threshold voltage determines whenever your bit will flip. This is how critical it is, right? Okay. So it all comes down to this equation, which now links, and I'm deliberately losing more, math, as you must have seen. Initially, we used to have more maths, and now we are losing. I'm just giving you the final product here. This is the threshold voltage equation, which you can derive. Don't have to. Which links flat band voltage, which shows that flat band voltage is a parameter in the equation that defines threshold voltage. And inside flat band voltage, so that means by changing flat band voltage, we can change the threshold voltage. Okay, that's a take-home message. We can change the threshold voltage. Sure, great. Okay, but how can we change the flat band voltage? Let's go back this slide. What are our options? You can either ask the oxide to change its trapped ion charges, which we cannot do because it's random. We could also change the oxide thickness, which we don't want to. It leads to unwanted consequences. The easiest thing that we could do ideally is change metal semiconductor work function difference. Now go back to the metal semiconductor work function difference equations. Let's uncover them. Phi m is given material parameter, chi is material parameter, band gap is material parameter. We cannot do anything about it. Only thing we can change is this phi fp or phi fn, depending on which type of semiconductor you're dealing with. Okay, sure. Okay, let's dig deeper and go back and see how are they related to doping concentration. This is how they're related to doping concentration. So basically you can change the doping concentration and you can fine tune phi fp, and thereby you can fine tune phi ms, thereby you can change phi f flat band phi fb vfb, and thereby you can change the threshold voltage really nicely. You can tell me how much threshold voltage you need and we can give it to you. Now I will take a step back from slides and tell you the significance, because it doesn't sound like it. Significance of this understanding. How many of you have used low power mode in your cell phones? Okay, or computer per se. Whenever you're running out of charge, I need to save battery, push a button, saves charge. What happens? Have you ever wondered what happens when you do that? Second question. There is a difference between the processors that are used in your laptop and the processors that are used in the supercomputers at Oak Ridge. They might even Core i7 for your laptop may not be the same as Core i7 for a desktop. I don't know if you have ever noticed that. Things are much faster in a desktop PC than a laptop. Why is that? Have anybody wondered? More power. Okay, you're right. Apparently, I haven't showed you that yet. This is coming up. Like, you see, everything is linked together. I have that end product in mind. I cannot show you right away because it's going to be too misleading otherwise. Threshold voltage is linked with how much current a transistor will draw. It is not just linked with when it will turn on. It is also linked with how much voltage. If your threshold voltage is 1 volt, you need at least 1 volt to turn on the transistor. If it is 0.5 volt, you could easily turn it on, right? So if you want to deal with low voltage applications, you reduce your threshold voltage. So basically, in any semiconductor foundry, any semiconductor company that makes chips, they have different flavors of transistors. LSTP, low standby power, HP, high performance. Basically, two major. There are other kinds which I'm not getting into. LSTP and HP. High performance variants, they could be identical otherwise, but HP variants, they offer two kinds. Which one do you want? Black or white? Like, getting a car. Similar. They give you two options. Maybe you are AMD making supercomputer for ORNL, or maybe you are, Apple making the next generation smart watches. So smart watches need to be low power because you don't want to keep charging them. So maybe Apple will choose for that product LSTP. But for Apple's Mac Pro, which needs to be used in gaming and stuff, they might choose HP. So they pick and choose which transistor to use to design the same circuit. Everything else is same, but your underlying transistors will have different threshold voltages. The only thing that is different between LSTP and HP will be VTH. High performance has lower threshold voltage, low performance has higher threshold voltage. So you need to be able to tune your threshold voltage accordingly. That's not the only thing. This is simple for you to understand. So I'm giving you that pitch. Okay. Now, when you use your lap like iPhone, and maybe it's running out of charge, you select low power mode. There is a way to change the threshold voltage dynamically, which I haven't showed you yet. So all that happens is it changes the threshold voltage from low to high. When you have higher threshold voltage, things become slower, but it also consumes less current. So you save battery. If you switch back, it changes the threshold voltage. So all of these features are all about changing threshold voltage. There are many other circuit techniques. If you take a circuit design course, including say 433, you'll see how critical it is for us to change the threshold voltage. Okay, so in circuit level, and I told you about levels of abstraction in this course, device, circuit, system. You might be a system designer or a circuit designer, agnostic to all these underlying boring phi ms, blah blah blah, right? But you need to change the threshold voltage in your circuit. If you have ever designed a circuit, this guy needs to have that threshold voltage, that guy needs to have that threshold voltage, especially in analog design. All sorts of threshold voltage required. When you send out the design to the foundry, they have to figure out a way to give you exactly that threshold voltage, right? 0.273 volt, 0.38 volt. Basically, that's how much resolution that they can provide. They could get to millivolt resolution. The foundry is in that stage. At least when I interned, I realized, oh wow, you guys could do that. Control 1 millivolt. They have that much control. You tell me how much millivolt or volt threshold voltage you need, we'll give it to you. Does that make sense? And they do all this by using this like seemingly simple phi ms tuning, metal semiconductor work function tuning. That's the easiest thing to do. Would you hardest thing to change metal, like change instead of gold, use copper. It's easy to say, but all of your tools, billion-dollar tools, are set for copper. You're not going to switch over to silver tomorrow, right? Not going to happen. Silicon is here to stay. You're not going to change it overnight. So the only thing that you could do is change your doping concentration. So all of these circuit design techniques that we'll talk about, like in 433 and other courses, or maybe you learned already, will all rely on changing the threshold voltage. That's all with me so far. And basically, the only thing that we could change in the okay, let's see what else can we change here. Phi FP is basically inside VFB. This is all the same. And no other parameters can be tuned at will to change the threshold voltage except for phi ms, essentially. All with me? All right. Now, so this is where we revisit threshold voltage. And let me tell you what happens at threshold voltage one more time using a different diagram. This is charge distribution diagram. And I'll probably ask you, this will be one of the questions maybe in the final exam. So I'm giving you a hint. So pay attention. This is flat band. This is not. How do you know? How do you know? No charge in the semiconductor. So it must have been flat band. And there is charge in the semiconductor. So it's no longer flat band, right? Okay, tell me one thing. If you apply positive voltage to the gate, what kind of charges will pile up here? Electrons or holes? Who likes positive? Electrons, right? And you see electrons will come all the way and say, hey, let's go. And they will pile up close to the surface. So you have negative charges. That's why when you apply positive voltage, we show that the charges in the metal are positive, upper half of the y-axis. But the charges in the semiconductor below the, in the lower half of the y-axis, that means it's negative. That's why we're drawing it this way. Everything has meaning. All with me? Okay. One other thing. Why is it thicker? Why is it like, so the more voltage you apply to the gate, this layer keeps getting thicker, not higher, but thicker. Why is that? Basically, the more voltage you apply, the more bending you get. Okay, the more bending you get. So this layer, this is the depletion layer. The depletion layer gets deeper and deeper. Making sense? And we discussed all of this in the last lecture, by the way. But the problem is there is a huge gap. I know that it's not probably making sense, so I'm repeating it again. So that's the reason why this thing extends inside. So it basically keeps getting bigger and bigger until when? Until the threshold inversion point. What happens at threshold? Remember, at the surface, the semiconductor essentially becomes N-type instead of P-type. So at that point, you start creating an inversion layer. So that's not shown here in this diagram. You only see up to the depletion layer. But that tells you this is the threshold inversion point, which is the maximum depletion depth. After that, it no longer extends anymore. It will actually start getting up. And I'll show you that in the next slide or next day. Probably we're running out of time. Let's see. This is actually last slide of this lecture. If you give me 1 minute, I can just finish this up, right? Doesn't make sense to. Thank you. Thank you. So this brings all of these concepts together. Let's just talk about just one side, and the other will be obvious. This is the full equation for threshold voltage. What is QSD max? This is the depletion charge that you're generating. This is QSD, depletion charge that is being piled up. Why is it max? Because at threshold point, you reach the maximum depletion. After that, it no longer depletes. It deals with electrons because it has inverted itself now. Okay, that's why it's called maximum depletion charge. Okay, QSS is the trap charge in oxide, which we don't really deal with too much. In math problem, you see oftentimes for simplicity, we'll assume it to be 0. Oftentimes. But if you know it, you can just plug it in. Oxide thickness is the thickness of this oxide. Epsilon ox is the dielectric constant of this oxide. It's related to that. You cannot change any of that. These are all given, right? Phi ms is the only parameter that you could change. So let's talk about phi ms. What's inside phi ms? We have already discussed this equation. We have already discussed phi fp can be changed by changing doping concentration. So you see, you know all of this. This is just a repeat of what we have discussed so far. And the same argument applies to the N-type semiconductor instead of P-type semiconductor. Similar equation, but instead of Fn, you have Fp. Wherever there is P, there is N. That's all. So that concludes this lecture, and we can start fresh in the next class. Thank you for giving me 1 extra minute.